Hello. In the video of today, I will describe a result that can be used to characterize Carnot-Carathéodory geometries. The theorem that I will present has been proved by Valery Berestovskii in 1986. The result has many implications, which we are going to discuss in the video after this one. However, the strongest statement is going to be that whenever we have a geodesic metric space that is topologically a manifold, and for which every 2 points A and B there exists an isometry sending A to B, then the metric space is a Carnot-Carathéodory space. Okay, let's discuss this result. We're going to start in a setting where all the smooth structure is already present. So the setting is going to be the following. So we have G, a Lie group, and we're going to have M, a manifold, and we are going to assume that G acts on M smoothly and transitively. Transitively means that for every 2 points in M there exists an element of G that is sending the first point to the second point. In other words, there is just one orbit in this action. Okay, what does it mean, action? Okay, maybe I will be more precise. So there exists a map that is phi, that is going from G cross M into M, a smooth map, such that when you see it as a function of G, so G in G goes to the map phi G as a map from G to G, these are really diffeomorphisms of M, and this map from G to the group of diffeomorphism, this is a group morphism. It's a group morphism. This is what it means to be an action. And transitive means that for all, so this is by definition, for all P and Q in M, there exists G in G such that phi G P is equal to Q. So we are going to say G as a map inside scene. We are going to identify G with this map here. So this map sends P to Q. Okay. Since, okay, this is a Lie group structure acting transitively, then one can fix a point and look at the stabilizer of that point, namely all those points in G that fix this point. And then that is going to be a closed subgroup. And the map G modulo this stabilizer will be homeomorphic to M. So equivalently, this action, this transitive action, is the same of saying that M has the structure, actually it's a unique structure of G modulo H for some subgroup H in G. It's a closed subgroup. Okay, so this is our setting as from the manifold point of view. Now let's consider a distance. So now let D be a distance function on M, and there is the compatibility on the topology, so that we are going to assume that induces the manifold topology. on M. Okay, now the assumption that relates G, the presence of this action of G and the distance, is that the action G on M with this distance d is by isometries. In other words, every map phi G dot, this is an isometry of the metric space MD. Yeah. Distance preserving bijection. Okay, we are already ready to state the theorem that we want to discuss. We will not prove completely, but I will explain some parts. Berestovskii from 1986 or 88 says the following. Okay, suppose as before, okay, we have G Lie group, M, so G close-up group, or no, okay, let's say M is a manifold metrized by a geodesic distance. So namely, this metric space now is going to be assumed to be a geodesic metric space. Okay? So this is a big important assumption. Now the next important assumption is that the action G acts on MD smoothly, transitively, and by isometries. So we would call MD a geodesic manifold that is homogeneous, a homogeneous geodesic manifold. The conclusion is that then the distance d is a Carnot-Carathéodory distance function. So MD is a Carnot-Carathéodory space, it's a CC space. Namely, what is it that our claim? Let's make the conclusion a little bit more explicit. So namely, we need to prove that there exists a G-invariant subbundle delta in the tangent space of M. There exists a G-invariant norm on Tm, such that D is really is equal to the Carnot-Carathéodory distance function associated to delta and the norm. And implicitly, I'm saying that I'm stating also the fact that delta is a Lie bracket generating subbundle. Otherwise, the distance would not be even finite. Okay. All right. So let's discuss a little bit the proof. Okay. Toward the proof. Okay. So we need to construct this delta and the norm. And for doing this, there is a step in the proof that this is going to be extremely important. I'm going to set it now. We shall prove the crucial inequality that D is greater or equal than some Riemannian distance, where dr is some G-invariant Riemannian metric. Now, on the one hand, this is necessary, right? Because if this has to be a sub-Riemannian distance, then, or a sub-Finsler distance, then there is a Finsler distance associated for which the sub-Finsler distance is greater, right? And now on a space G modulo H, actually all the Riemannian and Finsler distance are all by Lipschitz equivalent, because they only depend on what's happening at one point. So it's clear that whenever you choose one Riemannian metric up to multiplying by a constant, we expect this to be true, okay? But let me explain how many consequences, or what the important consequence of this inequality is. Instead, consequently, so if we have this, this inequality, if gamma now has finite length respect to d, so let's call it d length. Okay? So remember, d is a distance that is continuous. You didn't use the same topology, but could be really strange. And the curves of finite length might be also be strange. But because of this inequality, then gamma has also finite length with respect to dr, because the length with respect to dr is going to be smaller. No? Finite dr distance, and which means that is a rectifiable curve in the Riemannian sense. And rectifiable curves are, when you parameterize them by arc length, they are Lipschitz curves, and therefore, by Rademacher theorem, they are absolutely continuous. So I will just write, hence, there is up to reparameterization, but by Rademacher theorem, gamma is absolutely continuous. So we didn't know anything about the regularity of the distance, but at least now we know the curve of finite length are differentiable almost everywhere. And this will help us in defining what they should be, the horizontal vectors and the horizontal vectors of length less or equal than 1. So one can declare that a vector is in the distribution delta, or say V in Tm is in delta, and let's say with the length equal less or equal than 1. So right, this if and only if, so this will going to be a definition, if V is the derivative of a curve times 0 for some curve gamma defined in a neighborhood of epsilon, value into m with distance d, and this curve is a one Lipschitz curve. I'll go back to this point after I will prove this important inequality. But you see, if you take any one Lipschitz curve, and this is a geodesic space, so you have plenty of curves, non-constant curves that are one Lipschitz, and because of the inequality, they will be differentiable almost everywhere. So we will have many vectors that satisfy this property. Okay, so this was to say that that crucial inequality is very important. Okay, so let me spend now some time to really give a proof of this fact. So let's suppose we have dr G-invariant distance on this homogeneous space G mod H, or manifold M, and assume that dr is any Riemannian distance, and the d is a geodesic distance, giving the manifold topology. Then, okay, I cannot say that dr is less than d in general, but up to the multiplication are constant, then the constant, maybe let's put a constant here. Okay, it doesn't matter. There exists constant c greater than 0, such that we have this inequality. So up to changing the Riemannian distance multiplying by c, and this is again another Riemannian distance, there exists a Riemannian distance smaller than our initial distance d. Okay, I will prove this proposition with just one extra auxiliary assumption, that H is trivial. Okay, actually, after you prove it, after you understand the proof, you will understand that one can fix one can easily consider the general case. So a proof in the case H is trivial. Actually, if I can give a suggestion, then one should prove this this proposition first when you are in the space R2, right? And then in which you will really prove that that you have a distance coming from a norm. Okay, so we will do the Lie group case now. Okay, so what we do, okay, let's fix a norm on the Lie algebra G, and we know that locally the exponential map is a diffeomorphism, say, so such that on the ball of radius epsilon, this is the ball in the space G with norm of radius centered 0 and radius epsilon. This so on this ball, exp is a diffeomorphism with the image. Okay, for just technical reasons, just let me enlarge a little bit the ball, something like 7 times epsilon, just to be sure. Okay, so bigger ball. All right, now up to shrinking a little bit the ball, since X is a smooth map, the map becomes, the exponential map is a bi-Lipschitz map. So exp from the ball, maybe shrinking a little bit, so I say 2 epsilon, with the norm and the image exp p 2 epsilon with the Riemannian distance. This we can say is a C1 Lipschitz, actually bi-Lipschitz. I'm just using the fact that smooth maps are locally, diffeomorphisms are locally bi-Lipschitz maps. Okay, so let me write it. So 1 over C1 of norm of V is less or equal than the distance. So in particular, maybe I should say in particular, I will just look at the distance from the origin. X of V less or equal C1 norms of V. This is for all V that are in the 2 epsilon ball. Okay. Now, let's use another. Now I'm going to use the fact that the distance is giving the same topology. Now, note, since the gives the sense topology. Actually, in particular, it's a continuous function with respect to the manifold topology. And we also have the element 1 of the group. This is 1 of the group. 1 is not in the closure of this annulus exp b2 epsilon minus b epsilon. So we have this b epsilon, b2 epsilon. So right, the distance from 1 to a point in here is bounded from below. And also when you look at exponential coordinates, this is bounded from above. So then both the norm and the distance from the origin, or in exponential coordinates, these functions admit maximum and minimum on this annulus b2 epsilon minus b epsilon. What we have is that then there exists a constant C2 such that so if I write V divided by the distance x V, right? I want to say that this admits a maximum. So let me write this is less or equal than C2. So let me just bring it on the other side. So we are going to have this inequality. Okay. So, and this will be true for all V in the B2 epsilon ball minus B epsilon. Excellent. Okay. We have this inequality and we're going to use it soon. Right. So now we are ready to prove the bound for the distances. Okay. So now take any point. Let's start for points in the image of the epsilon ball. Now, we're going to write P as, so we are going to use this annuli that we have to cover by shrinking all this set. Namely, you can write B as the exponential of V over N with V in the annulus B2 epsilon minus B epsilon, and N a natural number. Okay, we can write it P in this form. Now, some observation. Okay, so first of all, if I take the power Pn, so exp of V over N to the N, this is, since exp is a one parameter subgroup, then this is just exp V. Then therefore, okay, but now what about if we look at the distance from 0 to P square? Let's start with the P square. Now, by triangle inequality, this is less or equal to the distance from 0 to P plus the distance from P to P square. Now, let's use the fact that we have a G-invariant distance. And therefore, this is equal to P 0, P. What I did, I multiplied both by P minus 1. Okay? So we got twice the distance between 0 and P. Okay? Of course, you can do this for n elements. So the distance between 0 and Pn is less or equal than n times the distance from 0 to P. Okay? Now, we know what is Pn in our case, this element. And we're going to use this inequality very soon. Okay. Now, therefore, the Riemannian distance between 1 and p, so p, we said we wrote it as exp of v over n. Now, I'm going to use the fact that this point is in the epsilon ball, and therefore I have the Lipschitz bound. So this is less than C1 norm of V over N, which of course is equal to C1 over N norm of V. But now V, we took it in the annulus. So we have the bound up to multiplying by C2, this an n, up to multiplying by C2, this is equal, less or equal than the distance from 1 to exp of V. So where we use the second inequality. And remember, this object here is p to the n. So now, with the triangle inequality, we have C1, C2 of n, and here we have n times the distance from 1 to p. So the n cancel, and we have C1, C2, distance from 1 to p. Okay, so we prove that up to this constant, the Riemannian distance is less than the unknown distance d. Okay, but this was only distance from the origin and for an epsilon ball. But now let's use the fact that these two are geodesic left invariant distance. Okay, now since both d and dr are left invariant or G invariant, let's write G invariant, and geodesic, the estimate, the same estimate holds globally. And this is the end of the proposition that said that our homogeneous geodesic distance is greater than some Riemannian distance. Okay, so let's now revise the construction of the Carnot-Carathéodory structure in Berestovskii result. Okay, so construction in Berestovskii result. Okay, so let's remember that we have proved that the distance is greater or equal than some Riemannian distance. So if gamma from I to MD is 1 Lipschitz, then same curve, but now when in the target we consider the Riemannian distance, since this is even smaller, this is still a 1 Lipschitz curve. And therefore, by Rademacher, gamma is absolutely continuous. Okay, so now let's define the subbundle of the tangent bundle. Okay, so let delta at p, defined like this. It is the derivative at 0 of curves where gamma is a derectifiable curve passing at time 0 at p. Okay, and of course one should be precise and one should write such that gamma dot 0 exists. Okay, If does not exist, then you don't consider this vector. Okay, so this is a space. Okay, and now because the geometry is G-invariant, this the collection when p varies of all this delta p is going to be a G-invariant subset of the tangent space. Okay, so far we don't really have a structure, and we haven't proven a structure. But let me, inside this space, also define what are the vector space of length 1. So, and let's define BP, or maybe it should be a posteriori. This is going to be the ball inside delta P with respect to some norm that we will construct, center at 0 with radius 1. This is going to be all those vectors, same story. So like gamma is a curve passing at P, differentiable at the origin, and gamma is a one Lipschitz curve with respect to D. Okay, so only the derivative of the one Lipschitz curves that are differentiable at 0. One at this point needs to prove a lot of properties about delta and B. Okay, so important things to check. So first of all, one should realize that BP is non-empty and compact. Now, the fact it's non-empty should be clear because there are curves, since the distance D was geodesic. Okay, maybe I'll write something about this. So D is geodesic, which implies that there exists non-constant one Lipschitz curve, and these curves which are absolutely continuous, so differentiable almost everywhere, and up to translating the time, one can assume that the derivative is at time 0. Okay, and this derivative, of course, also not only is non-empty in the sense that, okay, of course, you always have the 0. So maybe I should not write non-empty, but it's not, is different than just 0. And okay, if you have a geodesic, then the derivative cannot be 0 everywhere. Otherwise, it's going to be a constant curve. And now, since we have homogeneity, as soon as we have one non-zero vector at one point P, then you have at any other point P prime. Okay. The compactness comes as a consequence of the fact that the distance induces the same topology. But maybe I will not say more about this because I want to explain the next point better. So I want to say that BP is really a convex set. Maybe I will postpone this. Yeah, let me finish the proof and the list, and then we go back to the convexity. What is also obvious is by the definition is that span of BP is delta P, because every curve that is rectifiable up to shrinking time has one Lipschitz. And so up to dilating, every point in here will go here. Okay. So really, this is really like the cone on BP. Now, when we prove all this property, so and maybe I will also write and BP is star shape. Okay, but that's come as a consequence of being convex. Okay, that's even stronger. Okay, but after we have these three properties, then what we have is that BP is the unit norm, the unit ball for some norm on dp, and that's the norm that we will take together with delta to define the Carnot-Carathéodory structure. Now, let me say some things about why BP is convex. Why is BP convex? This is interesting because here it's one of the instances where it is very important that the geometry is homogeneous. It's homogeneous. Okay. It's okay. Say we have two curves or two vectors that come from curves. So we have gamma 1 and gamma 2, one Lipschitz curves with x1 equal gamma dot 1 0, or say I equal to 1 2. Then we want to find another one Lipschitz curve with derivative equal to the average of x1 and x2. And what we are going to do, we will perform a zigzag. Okay, I will do it with a picture. Okay, so let's say we have P, and then we have the curve gamma 1 and the other curve gamma 2, okay, whose derivatives give me x1 and x2. Now what I'm going to do, I'm going to fix some number n, and I'm going to consider the point, say that this is the point gamma 1 at time 1 over n. Then what I'm going to do, I'm going to translate by the left translation. So I'm going to bring this segment to this segment, or like this piece of a curve to this piece of a curve, by the isometry that sends P to this point Q, okay? And then I will attach this piece of a curve to this one, and I go to get two pieces of curve, okay? So this is going to be a isometry G1 applied to gamma 2.1 over n. After that, what I do, I take again the first segment that I was considering, and I translate it to attach to the point that I found. Now it's going to be G2 of gamma 1 of 1 over n. So what I'm going to do, I'm going to take these two segments per time 1 over n, and I'm going to perform a zigzag using the left translations, okay? Now, as n goes to infinity, the sequence of curves, now all these curves are pieces of one Lipschitz curve, and therefore they are one Lipschitz. So by Ascoli-Arzelà, they converge up to subsequence. So see, they sub-converge by Ascoli-Arzelà. Now, the claim is that the zigzag has the right derivative. So claim every limit is differentiable at 0 with derivative the average x plus y over 2. Let's go y. No, it was x1 and x2. So x1 plus x2 over 2. Okay. Now, how does one prove something like this? I'll just sketch it. So first of all, do this for lines. Okay, so convince yourself that if you take two lines in the plane, and then what you do, you follow by epsilon times the first line, and then epsilon second line, and so on. And then you do it for an epsilon that is smaller. Then, and so on. In the limit, you will get a line, and this line is parameterized with the speed that is, or like the derivative at 0 is the average of the derivatives. Okay, one does this exercise first, and then after that, what one has to observe that this calculation that one has just done, it only depends on the first order expansion of the action. What's important is the expansion at first order. Right? We are calculating the derivative of a curve, okay? And now it is true that these curves are not lines, but they're tangent to lines. It's true that the translation by elements is not a translation in the abelian case, but up to first order, like in the 0, it is first order is a translation, order 0 is a translation, and the first order there is a differential, but this differential is close to the identity because the action is smooth. Okay, so because of this this property, one has the vector, the space of unit vectors is convex. Okay, I'll go faster. Okay, so let's say that now we have a candidate subRiemannian distance. Okay, so we have a CC distance DC. Okay, so it is really coming from a subbundle with a norm. Okay, everything is G-invariant by construction. Okay, so what we want to prove is that DCC is equal to the initial distance. Okay, so one inequality is extremely easy, and the other one I will explain a bit. Okay, so DCC less or equal than D is easy. Here's the proof. Okay, so take any gamma, take any gamma, let's say 0t to m with unit speed respect to d. Oh, one Lipschitz. No, let's take unit speed. So t is really the length. Okay, but then this implies that that gamma is 1 Lipschitz with respect to d and also dr. And by construction, the derivative at every point is less or equal than 1. Okay? This is by construction of the norm. So the CC length of gamma, which is the integral norm, the derivative, 0t, this is less or equal than the integral from 0 to t of 1, which is t, which is the length respect to d of gamma. So we prove that DCC is less than d because they are geodesic distances. Okay, so now the other inequality is a little bit harder. So more difficult direction. So d less or equal than DCC. I will sketch only a little bit the argument. an argument. So take 2 points, P and Q, in the manifold, on the group, G mod H. Now take CC geodesic, gamma. So say gamma, say from 0 to T to M. Now, just for simplicity, assume it C1, of course, up to an error, you can do that. Now, what we need to do, we need to find a curve for the distance d that is whose length is comparable to t. And okay, so we have to come up with a curve. Now, the fact is that we have this curve gamma, but we don't know initially that the curve gamma is even rectifiable for the distance d. What we know is that for every point of differentiability, when you take the derivative, then you know that there exists another curve, let's call it sigma, whose tangent is the vector. But so the curve gamma meets another curve sigma that had tangent respect at the same point with the same vector. But the curve might be different. So, but what we now need to do, we need to constantly approximate for different points the curve with some zigzag curves. What I wanted to say is that we need to prove that the curve gamma does not have a CC length that is much shorter, or that is shorter than the D length, the D distance, so between the extreme points. Okay, so for this we will construct a zigzag curve. Okay, so that's the plan. Let's start. So what we do, we divide gamma into n equal parts, and we'll go to infinity. And what we do, okay, we start from P. And what we do now, we know that the vector gamma dot 0, this is norm 1, or less or equal than 1. Then, therefore, there exists some curve sigma, it's currently sigma 1, with exactly the same vector, tangent vector, so passing at the same point with the same vector. And sigma 1 is 1 Lipschitz. Okay, and we follow this curve up to time sigma 1 of time t over n. T was this value here. Okay, now what we want to do, we want to continue. And we want to continue in a similar way than the point gamma at time 1 over. So here we might have the point gamma of time t over n. Okay, but no, these 2 points are different, but they're close to each other, because you see these 2 curves were tangent, right? So for n large, they are close to each other. So what we could do, we could see this tangent vector at this point close to a tangent to a vector here, still of unit length. And then we can find another curve now for this Lipschitz respect to d in the direction of this vector. Okay, so since gamma dot t over n is also norm less or equal than 1, then there exists a curve sigma 2, again a 1 Lipschitz curve, with Now we will start the starting point at time tn is the one we were before, and the tangent vector at Tn is not equal, but is very close to gamma dot at time T over N. Okay, we're going to have this. And then what we do, and then we take this curve, which is sigma 2, and we up to the point twice Tn. And we will continue up to arriving a point that is should be close to Q, the final point, and this point is sigma n, or sigma n of t, because we are going to do it n times. So iterate n times, and get so up to at the point sigma n t. Now it should be expected that by some inequality, and one can actually use Grunwald inequality or some variant, the sigma n of t should converge to the point Q. Q was the final point, yes, the final point we called Q. Should converge as n goes to infinity. As n goes to infinity. So let's bound, instead of the d distance between between P and Q, the distance between P and sigma n t. So what we have is that the distance between P and Q, this is more or less distance between P and sigma n t. Now so this was the final point of a zigzag curve. So triangle inequality. This is the sum of the distance between the ith curve time I minus 1 over should I put I 1 n, okay, I over n, okay, multiplied by t, okay, okay, I should go from 1 to n, sigma n, sigma, yeah, should be correct. Okay, so these are these points here, tick, tick, and the final one. Okay, right, now each of them, each sigma was a one Lipschitz curve, so this is less or equal than, okay, we're going to have n times the same bound, so this is the sum, okay, let's still put the sum of I minus 1 over n times t minus I over n times t, which is t over n, so it's n times t over n, which is equal to t, which was exactly the distance between P, the CC distance between P and Q. This concludes what I wanted to say on a sketch of the proof of Berestovskii theorem. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel, clicking below.